Have you ever wondered if you could build a universe from scratch? Not with stars and planets, but with simple rules and a handful of pixels. What if I told you that inside the glowing screen of an old computer, you could witness entire digital worlds being born, evolving, and fading away, all from a few lines of code? These aren't just random flickers of light. They are intricate, mesmerizing patterns that grow and change like living things. Imagine a cascade of triangles forming a perfect fractal, or a swarm of tiny digital gliders cruising across the screen. This is a world where complexity arises from utter simplicity, a place where we get to play creator and see what happens. It's a grand experiment in digital biology, and it's one of the coolest things you can do with a computer. We're about to dive headfirst into this hidden cosmos. We'll watch as simple starting points, just a few lit-up pixels, explode into structures so complex they seem to have a mind of their own. Some will form stable, repeating shapes like digital crystals. Others will generate endless, unpredictable novelty, forever expanding into the unknown void of the screen. This is the magic of emergence, where the whole becomes so much more than the sum of its parts. It's a process that feels deeply fundamental, echoing patterns we see in nature, from the formation of snowflakes to the flocking of birds. It's a rabbit hole of discovery, and I invite you to fall down it with me. Let's get our hands dirty and build a universe. This journey isn't just about watching pretty patterns, though. It's about understanding the engine that drives them. We're going to explore this digital genesis not on a modern supercomputer, but on a virtual recreation of a humble, classic piece of hardware. This constraint is where the real fun begins. It forces us to be clever, to be resourceful, and to appreciate the sheer elegance of making something amazing with very little. We are not just observers, we are digital archaeologists, uncovering the secrets of computation by using the tools of the past. The limitations are not a bug, they are a feature, and they make the final result all the more satisfying when it finally flickers to life. Our quest is to unlock the secret universe of cellular automata, but we're doing it the hard way and the most rewarding way. We'll be firing up a virtual 6510 microprocessor, the brains behind one of the most beloved computers of all time. By building our world on this classic chip, we connect with a golden age of computing, a time when every byte of memory and every clock cycle was precious. We'll see how these constraints shape our digital creations, forcing us to invent solutions and tricks that programmers from 40 years ago would recognize. It's a tribute, an experiment, and a whole lot of fun. Let's power it on. Let's talk about the star of our show, the MOS Technology 6510 microprocessor. If that name doesn't ring a bell, maybe its most famous home will... the Commodore 64. This little 8-bit chip, running at a blistering speed of just under 1 megahertz, was the engine for a generation of gamers, programmers, and hobbyists. It was simple, it was cheap, and it was everywhere. The 6510 wasn't the most powerful chip of its day, not by a long shot. It had a tiny set of instructions and could only handle small chunks of data at a time. But its limitations were also its strength. It forced programmers to be incredibly creative. Working with the 6510 is like building a ship in a bottle. You have a very small space and a limited set of tools. The processor only has a few registers, tiny little scratch pads for holding numbers, and it can only access 64 kilobytes of memory. That's not 64 gigabytes or even megabytes. It's 64 kilobytes. Your average smartphone photo is 100 times bigger than the entire universe a C64 could work with. This scarcity made every single byte a precious resource. Writing code for the 6510 was a puzzle, a game of optimization where you had to squeeze every last drop of performance out of the hardware. It was a true test of a builder's ingenuity. So why, in the year 2025, Would we deliberately choose to work with such an ancient and limited piece of technology? Because challenge is where creativity is born. Anyone can run a complex simulation on a modern computer with gigabytes of RAM and a multi-gigahertz processor. That's like building a skyscraper with a limitless budget and an army of cranes. But can you build something beautiful, something complex and emergent, using the digital equivalent of toothpicks and glue? That's a much more interesting problem to solve. The 6510 is our set of constraints, the rules of the game that make victory so much sweeter. Our main goal here is to explore the stunning complexity that can emerge from simple rules, and doing it on a virtual 6510 adds a fascinating layer to the experiment. We're not just creating cellular automata, we're recreating the entire experience of discovery from the dawn of home computing. We're going to feel the same limitations and hopefully experience the same aha moments that programmers did back in the 1980s. The patterns that emerge on our screen won't just be a product of the rules we define, but also a product of the hardware's soul. It's a beautiful collision of mathematics and history, and it's going to be awesome. All right, let's demystify this term, cellular automaton. It sounds complicated, but the core idea is beautifully simple. Imagine a grid of cells, like a giant sheet of graph paper. Each cell can be in one of a few states, the simplest being either on or off, black or white, alive or dead. That's the cellular part. The automaton part comes from the rules. At each tick of a clock, every single cell on the grid looks at its neighbors, the cells immediately surrounding it, and decides what its next state should be based on a simple set of rules. That's it. A grid, states, and rules. The most famous example, the rock star of the cellular automata world, is Conway's Game of Life. The rules are wonderfully simple. For each cell, you count how many of its 8 neighbors are alive. If a dead cell has exactly 3 live neighbors, it springs to life in the next generation, as if by birth. If a living cell has 2 or 3 live neighbors, it survives. But if it has fewer than 2, it dies of loneliness, or more than 3, it dies of overpopulation. Every cell on the grid applies these same rules simultaneously, and then the whole grid updates to the next generation. What happens when you press go? Pure magic. From these 3 simple rules, you get an astonishing variety of behaviors. You see stable patterns that stay put forever, like digital still lifes. You see oscillators that blink and pulse in a steady rhythm. And most famously, you get spaceships like the glider, a tiny 5-cell configuration that moves across the grid indefinitely. These aren't programmed to move. Their movement is an emergent property of the rules. No single cell knows it's part of a glider. It's just following its simple local instructions. This is the big, mind-blowing idea behind cellular automata. But the game of life is just the beginning. There are thousands of other rule sets, each creating its own unique universe. Some rules create perfect, self-replicating fractals that grow to fill the screen with intricate detail. Others produce chaotic, bubbling patterns that look like boiling liquid. A few create structures that seem to interact, build, and destroy each other like a complex ecosystem. By just tweaking the rules, say, changing the number of neighbors required for a cell to be born, you can jump from a dead, empty universe to one teeming with chaotic, unpredictable activity. It's a vast, mostly unexplored territory of digital physics, and we're about to go exploring. Running these digital universes on a modern machine is one thing, but trying to cram them into the tiny confines of a 6510 processor is another challenge entirely. Remember, we're dealing with a chip that runs 1,000 times slower than a low-end smartphone and has a tiny fraction of the memory. A 64 by 64 grid of cells, with each cell being a single byte, would take up 4 kilobytes of RAM. That's nearly 7% of the total memory available on a Commodore 64 just for the grid itself. This scarcity immediately forces us to think differently. We can't afford to be wasteful. Every instruction, every byte has to count. The 6510 slow clock speed is our next big hurdle. To update our grid, the processor has to visit every single cell, check its neighbors, apply the rules, and decide on the new state. For a 64 by 64 grid, that means thousands of cells to process for every single frame of animation. A simple, straightforward implementation in a high-level language would be painfully slow. We might only get one new generation every few seconds. To get the fluid, lifelike motion we want to see, we have to throw out the modern programming playbook and get down to the bare metal. We have to think like a 1980s demo scener. This is where the creativity comes in. How do you speed things up? Maybe you don't store the grid as a simple array. Perhaps you can use clever bitwise operations to check multiple cells at once. Instead of a full byte per cell, what if you could pack 8 cells into a single byte, using each bit to represent on or off? That cuts your memory usage by a factor of 8. But it also makes the code for checking neighbors much more complex. It's a trade-off. You're trading code complexity for speed and memory efficiency. These are the kinds of puzzles that made programming on old hardware so compelling. These constraints don't just make the project harder, they make the results more impressive. When you see a complex automaton running smoothly on a machine that by all rights shouldn't be able to handle it, there's a special kind of magic to it. It's a testament to the power of optimization and human ingenuity. The limitations of the 6510 become part of the art form itself. The final patterns are not just a product of the mathematical rules, but also of the clever hacks and workarounds needed to bring them to life on such humble hardware. The struggle is what makes the final display so beautiful. So, Conway's Game of Life gets all the press. But honestly, it's just one species in this vast and wild zoo of cellular automata. One of the most fascinating alternatives is the work of Stephen Wolfram, who studied the simplest possible automata one-dimensional ones. Imagine a single row of cells instead of a grid. Each cell's new state is determined only by its own state and, the states of its immediate left and right neighbors. Even with this radical simplicity, you get, mind-bending complexity. One famous example, Rule 30, starts from a single black cell and generates a pattern of complete, unpredictable chaos, yet with these strange, large-scale triangular structures embedded within it. Another amazing family of automata is called generations. These are similar to the Game of Life, but cells don't just die, they can age. A cell that is born enters state 1. In the next generation, if it survives, it moves to state 2, then state 3, and so on, often with different colors for each age. After a certain number of generations, the cell finally dies. This simple addition creates, honestly, breathtakingly beautiful and organic-looking patterns. Explosions of color bloom and fade, leaving behind intricate coral-like skeletons. It looks less like a computer simulation and more like a time-lapse video of a petri dish filled with alien microbes. Then there are rules that produce stunningly geometric and fractal patterns. A rule called B2/S234, that means born with 2 neighbors, survive with 2, 3, or 4, creates diamond-shaped structures that grow, replicate themselves, and tile the screen in a perfect, repeating pattern. Another one, known as day and night, has this beautiful symmetry. The rules for birth and survival are the exact inverse of each other. This causes the screen to fill with shimmering, oscillating blobs of black and white that constantly fight for territory, creating a dynamic balance between the 2 states. It honestly feels like you're watching a living, breathing yin-yang symbol. Exploring these lesser-known rules is like being a naturalist discovering new species. Each rule set is a new world with its own unique physics. its own flora and fauna. Some are barren and die out quickly. Others are overactive and explode into featureless noise. But in between are these gems, these just right universes that produce endless novelty and structure. Part of the fun of this whole project is simply being an explorer. We can plug in random rules, set an initial configuration, and see what kind of universe we've just created. It's a process of pure discovery, and honestly, you never know what you're going to find. To run our experiments, we don't need to hunt down a 40-year-old Commodore 64 on eBay. Instead, we can build a time machine in software. A virtual 6510, also known as an emulator. An emulator is a program that runs on your modern computer and pretends to be an old piece of hardware. It meticulously recreates the behavior of the original chip, down to the last detail. It has virtual versions of the processor's registers, the accumulator, or A, the X and Y index registers, and a block of memory that acts exactly like the 64 kilobytes of RAM the real chip used. The heart of the emulator is a big loop. In this loop, the virtual CPU performs a 3-step dance over and over. First, it fetches an instruction from its virtual memory at the location pointed to by its program counter. Let's say the instruction is LDA, which means load the accumulator. Second, it decodes that instruction to figure out what it's supposed to do and where its data is. For example, LDA number 16 means load the number 16 into the A register. Third, it executes the instruction, changing the state of its virtual registers or memory accordingly. Then, it increments its program counter, and the cycle begins again, millions of times per second. This process perfectly mimics how the real 6510 chip works. When we write our Cellular Automata program in 6510 assembly language, we're not writing code for our modern PC. We're writing it for this virtual chip. The emulator loads our program into its virtual memory and starts executing it, one instruction at a time, just as the real hardware would. This allows us to run vintage code with perfect fidelity. It also gives us some amazing superpowers that the original hardware developers could only dream of, like the ability to pause the execution, inspect the memory and registers, or even run the code backward. Of course, emulating a chip perfectly is a huge challenge. The 6510 had its own quirks and undocumented behaviors that are crucial for getting some software to run correctly. For our project, we also need to emulate the hardware that draws the image on the screen, the VC2 chip in the case of the Commodore 64. Our virtual 6510 needs a way to draw the state of our automaton grid to the screen so we can see it. This adds another layer of complexity, but it's also part of the fun. Building and using an emulator is not just an act of programming, it's an act of digital preservation and archaeology. Writing code for the 6510 is nothing like modern programming. You don't have fancy languages with helpful functions. You have assembly language, the raw native tongue of the processor itself. It's a world of 3-letter mnemonics like LDA for load accumulator, STA for store accumulator, and JMP for jump. You are manually moving bytes of data from memory into the processor's registers, performing a single operation, and then storing the result back into memory. It's incredibly low-level and requires you to manage every tiny detail yourself. It's like performing surgery with a pair of tweezers. To make our automata run fast, we have to choreograph a delicate ballet of data. A naive approach to counting a cell's neighbors would be slow. You'd load the state of the top left neighbor, add it to a running total, load the top neighbor, add it, and so on, 8 times for every cell. A much faster trick is to use lookup tables. Before we start the simulation, we can pre-calculate the result for every possible combination of a cell and its neighbors and store it in a table. During the simulation, instead of doing lots of math, the code just looks up the answer directly. This uses more memory, but it's vastly faster, a classic trade-off. Another classic optimization involves unrolling loops. A loop is efficient for writing code, but the act of checking the loop counter and jumping back to the start takes precious clock cycles. If you know you need to process, say, 40 cells in a row, you can unroll the loop by simply writing the code for processing one cell 40 times in a row. The resulting code is much longer and more repetitive, but it runs faster because the processor doesn't waste time on loop administration. This is the kind of brute force, cycle shaving trick that was common in the golden age of 8-bit game development. Self-modifying code is another powerful, if dangerous, technique in the 6510 programmer's toolbox. The 6510 doesn't distinguish between code and data. This means a program can actually rewrite its own instructions while it's running. For our automata, we could write a piece of code that processes a row of cells and then have it modify its own memory addresses to point to the next row before executing that section again. It's a wild and confusing way to code, and it makes debugging a nightmare, but it can lead to incredibly compact and fast solutions. It's the ultimate expression of treating code as just another piece of data to be manipulated. Now for the payoff. We've got our rules, our virtual 6510 is warmed up, and our optimized assembly code is loaded into memory. We hit the virtual run switch, and the show begins. On the screen, a simple line of cells flickers. We're running Rule 110, another one of Wolfram's one-dimensional automata. At first, it just looks like a messy, downward drifting pattern of black and white triangles. But as we let it run, something incredible happens. Within the chaos, stable structures emerge. We see clear lanes and, moving within them, persistent patterns that hold their shape. These are the gliders of Rule 110. It's amazing because Rule 110 has been proven to be Turing complete, which is a fancy way of saying it can be used to compute anything that any modern computer can compute. It's a universal computer made of nothing but simple rules acting on a row of cells. The gliders and their interactions can be arranged to create logic gates, the fundamental building blocks of a CPU. We are literally watching the components of a computer assemble themselves out of chaos. It's one of the most profound discoveries in modern science, and we're watching it happen on our virtual 8-bit machine. Next, we load up a generations rule called walled cities. We start with a small random blob of cells in the center of the screen. The simulation starts and the blob begins to expand. The outer edge is a fiery yellow, representing newborn cells. Behind it, the cells age through shades of orange, red, and finally a deep purple before dying out. The pattern grows in fits and starts, creating thick concentric walls with dark empty courtyards inside. It looks like the ruins of some ancient alien civilization seen from above. Occasionally, a glitch in the emulation or an unexpected interaction causes a wall to crumble, creating a new, unique feature. These mistakes are part of the charm. They make our universe feel unique. Sometimes the most interesting results come from bugs. In one run, a mistake in my neighbor counting code caused cells at the edge of the screen to wrap around and connect to the other side, creating a toroidal or donut-shaped universe. In the game of life, this led to a strange phenomenon where gliders exiting on the right side of the screen would reappear on the left, sometimes colliding with other patterns in unexpected ways. This bug created a completely different ecosystem. It's a perfect example of a happy accident. The quirks of the emulation aren't failures. They're unique features of our experimental setup, adding personality to our digital worlds. So what's the big takeaway from all this? We've seen that from the simplest possible ingredients, a grid of on or off switches and a few rules, we can create universes of staggering complexity. We've watched lifelike structures emerge, evolve, and interact. This simple idea raises a profound question. Could our own universe work the same way? Could all the complexity we see, from chemistry to biology, be the emergent result of a few fundamental, underlying rules playing out on a massive scale? We don't have the answer, but playing with cellular automata certainly makes you wonder. It's a powerful philosophical tool disguised as a computer game. Working within the tight constraints of the virtual 6510 taught us something else. It showed us that limitations are a powerful catalyst for creativity. When you don't have infinite memory and speed, you're forced to find more elegant, clever, and efficient solutions. This mindset is incredibly valuable, even today. In a world of bloated software and ever more powerful hardware, the art of optimization and resourcefulness is sometimes lost. Revisiting these old machines reminds us of the beauty of doing more with less. It's a fantastic mental exercise for any builder, maker, or programmer. This journey back in time to the 8-bit era isn't just about nostalgia. It's about reconnecting with the fundamentals of computing. When you code in assembly, you are in direct conversation with the hardware. You feel every clock cycle tick by. This deep understanding of how the machine actually works is something that's often abstracted away by modern tools. There's a joy and a power in peeling back those layers and working directly with the metal. It reminds us that at the end of the day, all the amazing things computers do boil down to manipulating ones and zeros in very clever ways. I encourage you to try this yourself. You don't need a degree in computer science. All you need is curiosity. There are fantastic emulators and simple programming tools available online for platforms like the Commodore 64, the Apple II, or the Atari 2600. Try loading up a simple Game of Life program and just play with it. Change the initial patterns. See what happens. Then, if you're feeling brave, try changing the rules. What if a cell needs 4 neighbors to be born? What if survival requires only 1? You are the physicist of your own pocket universe. Go discover something new. I promise it's one of the most rewarding experiments you can do.